Okay, we're going to get started. Welcome everybody to the results presentation for performance comparison of abutment and retaining wall drainage systems. If you're joining us on a webinar, your phone will be muted from our end, so we won't be able to hear you if you try to speak to your phone. All questions should be held until the end of the presentation, and then Julian Tao will go ahead and answer those for you. Julian Tao is with the University of Akron, and they have spent about 3 years on this project. And with that, I'll go ahead and turn it over to Julian.
Thank you, Patty. Good afternoon, everyone, and welcome to this presentation. So I'm Julian Tao from the University of Akron. So I'm very glad to share with you the results from the project titled Performance Comparison of Abutments and the Retaining Wall Drainage Systems. So this effort is put together with myself, a couple of graduate students, Junliang, Junliang, as well as Professor Robert Liang, formerly with the University of Akron, as well as 2 colleagues from the University of Wisconsin, so Ace and also Professor Akron. So at first, I would like to thank all the people who helped us and provided guidance and assistance along this way of this research. So first of all, from the technical committee, Jim, Sean, and Muhammad, and also site engineers Andrew, Dave, Brian, Matthew, and Jeremy from the contractor, and also a lot of workers that are there. Unfortunately, I don't have the name, but I know Bob, the inspector, was there. Thank you, Bob. And also Kelly and Michelle from the research office, who helped us a lot, and also student assistants as well as technicians at our university who helped us in the laboratory work. So this is the content about this research. So I will first discuss a little bit about the problem statement and the research objectives, and then followed with several tasks, okay, which is key from this project. So I'll start with the problem statement and the research objectives. So bridges and the retaining walls are very critical components in the surface transportation system. And if they fail, they can affect a lot of issues regarding the ride quality of the roads, disrupt the traffic, and also incur large road repair costs. So here are several figures showing the failure of abutments as well as some wing walls and the retaining walls. So there are a lot of reasons for the failure of the walls, but a major reason actually is related to drainage. So when there is a poor drainage, so the water can only accumulate behind the wall, so to increase the hydraulic pressure. Okay. So this hydraulic pressure actually will cause a lot of troubles. So first of all, when we design a wall, actually we have to determine the load acting on it. So the majority load comes from the earth pressure. But when you have water pumping behind it, so you have additional hydrostatic water pressure. So this will increase the load acting on the wall. On the other hand, water is bad because when you have larger water pressure, so it will reduce the effective stress inside the soil, as well as to reduce the strength and also change the deformation property of the soil. So it's a very critical matter. So we need to deal with this water. We want to drain them out. So currently, ODOT actually have specifications on this. So Item 518 specifies the use of a 2-foot porous backfill behind the wall and wrapped with a filter fabric. So this porous backfill is free draining. And it's specified, it should be conformed to Item 703, number 57. Okay, so pretty larger particle sizes, so it's free draining. And the function of the fabric is to help to retain the soil so that will not be washed away, and also to prevent the clogging of the soil on that interface, so that can ensure the performance of the drainage system. And both of these two materials actually are also specified. For the fabric, so we are using Adam 712.09 type A. And also in the bridge design manual, note 701.2, it also specifies the extension or the layout of this porous backfill placement at the bridges. But ODOT is seeking alternative drainage system which can potentially provide more cost and time effective method, and is also durable and have comparable and superior drainage capacities compared to the current practice. So one candidate is the prefabricated composite drainage system, or we call the PCDS. So that is proposed as an alternative. So the idea is we replace that porous backfill, so the gravel, with a prefabricated plastic, kind of a plastic material. Okay, so and we also have one layer of this fabric to provide a similar function. So here is a close-up look at a sample PCDS system. Okay, so as you can see here, the core there have dimples. So that dimples actually create a lot of void inside, so the water can drain freely. And on one side, it also have a fabric to bond it there. Okay, so to prevent declogging as well, to allow the water actually see. Okay. So there are different configurations about this system. There are a lot of commercial available materials. So here on the right is another example showing that you actually can have different types of this composite drainage system with different elevations. Okay. So on the top level, you can have a thinner one. On the bottom level, you can have a thicker one. So it's got a low profile sheet core, so it can have actually a larger drainage capacity, because all the water actually will eventually go down to the bottom. So at the bottom, you need a larger capacity. So this project is to help ODOT to assess the effectiveness of these two systems, and hopefully we can come up with new specifications for the second proposed system. So here we actually took 6 tasks. The first one is to do a statewide survey regarding the performance of the current systems and identify some potential issues. And the second task is to do a comprehensive literature review on the second system, so we can know better about the performance and the existing codes and the specifications used in other DOTs. And the third task is to do some testing in the laboratory and to evaluate the performance of these some selected products, so we can better understand which parameters we need to focus on these products. And then we go to the field and install these two systems side by side, and in the hope that we can compare their performance. And also we also check the cost of these two systems, so we can get a cost analysis and a comparison to see if we have any cost benefit from that. And the last task is to actually synthesize all the findings from the previous tasks, so to provide some recommendations regarding the development of the specifications for the new system. So I'll start with the first task, which is a state of practice survey. And we designed a questionnaire, and we sent out to 88 Ohio County engineers and 10 contractors as well. But we only received 34 county responses and 2 from the contractors. But still, they provide us a very good data that we can look on. So as you can see on the left-hand side figure is a summary about the usage of the drainage system in Ohio. So the majority actually is the specified method, which is a porous backfill with a filter fabric. But there are still a big chunk who are using actually the porous backfill without the filter fabric. We identified one response which mentioned the use of the prefabricated composite system, but only one case. And also there are some other non-traditional methods, including, for example, the low-weight motor. So that's a summary about the current usage. And on the right-hand side is a kind of preliminary cost summary. Okay, so for the porous backfill with the fabric, so the average cost, unit cost is between $50 to $80 per cubic yard. And I'll show you what it will cost for the second system a little bit later. Regarding the performance of these systems, we identified that the engineers and the contractors are actually very happy with the performances. For porous backfill with filled fabric, so the performance is about very good to good, and for without filled fabric, it's good to very good. So in general, actually, with fabric, filled fabric actually provide you a better performance, but they are all pretty good in terms of performance. And we also identified some potential issues regarding these systems. So the most reported are the clogging, either at the weep-hole or the drainage pipes, and also the erosion behind the walls. Okay, so actually these are due to the fabric. Okay, so if you don't have that fabric, you cannot prevent the erosion and clogging to occur. So the fabric is pretty important. And also in terms of maintenance, actually they found it's pretty challenging to maintain the drainage pipes and the outlets, which are actually embedded in the soil. So even though they found the clogging, but they cannot do too much about it. And in terms of the challenges during construction, so the response are placing the filled fabric is actually most challenging for them. And another one is actually it's difficult to control the quality when they build up the two-foot porous backfill layer. And also we also asked them if they would like to have an alternative drainage system, and in general they actually expect some benefit from that system. So of course you can say anything about the benefits, the cost savings, labor savings, and easier ways to control the quality, so on and so forth. So a brief summary about the first task. So porous backfill drainage systems with or without the fabric are predominant drainage system in Ohio, and the performance of the traditional drainage system is actually satisfactory in general. But the observed problems of the systems including clogging and erosion of the soil. And the installation of the fabric, as well as the quality control and assurance of this construction, is pretty challenging, reported by the respondents. And also, they also generally advocate that the usage of the PCDS, if they can bring such benefits as a lower cost, the labor saving, and a simpler construction process. So after that, we want to learn more about the alternative drainage system, but focus on the PCDS system. And here we reached out to different manufacturers, and in total we got 87 composite drainage systems from 17 manufacturers, and we believe that we covered the dominant products on the market. And here is actually a summary about the properties and the ranges of the properties reported to define the performance of these systems. So I will not go one by one, but I show you why they are important. So the core thickness and the core in-plane flow rate actually will ensure the drainage capacity. So that will tell you what drainage capacity can you expect from that product. And also the core compression strength actually will ensure that they will not be damaged during construction or during service. And regarding the fabric, there are more parameters, but these parameters actually also can be grouped into two categories. The first one is hydraulic property, including, for example, the apparent opening size, which is actually the largest pore size, okay, on the fabric. And fabric flow rate and the permittivity, so they are actually the similar things to define the drainage capacity. And also the apparent opening size also can help us to determine whether it can provide clogging resistance and to provide soil retention capacity. And the last three parameters actually are similar to the strength of the core, so that actually is to ensure the constructability. So we also looked into different design methodologies, and we summarized our findings here. So the majority of the major points in respect to design are the in-plane flow rate, okay, which actually can be done from flow night analysis behind the wall. And here Q actually is the drainage quantity, and it actually depends on the soil behind the wall, so how permeable the wall is, as well as the height of the wall. The higher the wall is, you will expect a larger drainage requirement. And also theta here means the transmissibility actually is just the ratio of Q over the I, which is the hydraulic gradient. Okay. So, but from Q to the designed value, which we can use to select the correct product, we need to do a lot of reductions. Okay. So we need to introduce a factor of safety to account the uncertainties of the site material as well as the construction process. We also need to consider some potential reduction factors, okay, due to the performance of these the drainage system. I mentioned that the drainage system actually includes a core as well as a fabric. So this fabric may intrude inside the core, so that we actually reduce the drainage capacity. Okay. So we actually found that there are several factors which can affect the drainage capacity, including the intrusion or the infiltration of the fabric into the core, as well as the creep deformation of the time-dependent deformation of the material, as well as clogging due to chemical or biological factors. Okay. But the takeaway information from this slide is, okay, the design of this drainage composite actually depends on the soil property, the height of the wall, as well as some reduction factors. And also for the strength itself, so it's similar to the strength requirement when we build the wall. Okay. So the force acting on this board after we build it, so they mainly come from the earth pressure. Okay. So it also depends on how high your wall is, and also how dense or how heavy your soil will be. Okay. And also another key factor is actually the T here, which is a lateral earth pressure. So the selection of the T is actually critical, and it depends on the type of the backfill soil and the structure. For conventional abutments and walls, you can use at-rest coefficient, T0, which is typically a low value, about 0.5 for most of soils. But if you are designing a semi-integral and integral abutments, where when you have the expansion of the deck, that will push the wall towards the soil, so you will have a larger lateral earth pressure. So this larger earth pressure, you can use a passive earth pressure, which is Kp, which is much larger than T0. So typically they are 2, 3, or 6 even. Okay? But we cannot use that because it's too large, and most of the case, passive failure actually won't happen. Okay? So we found a way to actually compensate that. So the allowable lateral movement of the top of the abutment actually is specified for most of the bridges. According to ASHTO, our FD design guidelines, so the limited movement is actually 1.5 inch. So from there, we can actually create the T that we needed to calculate that theta, okay, in terms of the displacement, okay, about the wall. So here is one correlation that we found, which will be very useful So this K will be larger than K naught, but smaller than KP in general. So regarding the fabric, you need to consider the permeability criteria. It should be permeable enough for the water to seep in, but it's also the opening size should be smaller enough to retain the soil. Otherwise, all the soil particles actually will go through. It also be larger enough to prevent the clogging at the interface. So you will have a range. You have a range of the opening size depending on the particle sizes. So there are different design methodologies, for example, from Federal Highway Research in 1998, or the actual M288 Class 2 actually also provides some guidance on the selection of the hydraulic properties. The fabric should also be strong enough, so to survive the construction and also the degradation during service. So ODOT right now is using 12.09 Type A for structure drainage fabric. So Type A was originally developed actually for under drains and slope drains. So these drains actually are embedded in a relatively shallow depth. And also during construction, actually, the construction machinery and the loadings are typically low. So we suggest actually to increase the levels or increase the safety of factor when we select the fabric for the structural fabric. So we think the actual M288 Class 2 will provide us a more suitable criteria for the fabric during the structural drain. So this recommends requires the strength properties for 4 classes and survivability. So class 1 actually is the most robust, and class 3 actually is the least robust. So current Type A from ODOT actually is similar to class 3. And class 2 is, we think is more reasonable for structural drains. When we compare these two criteria, we found that the current ODOT Type A actually has much lower required values than actual class 2. We also searched the specifications from different DOTs, and we found actually 21 state DOTs are using PCDS products, and 16 of them actually have specifications. 5 of them provide design guidance, and 10 of them actually specify the procedures during the construction as well. And also 7 of them provided approved the product list. So this actually, we summarize all the specifications by other DOTs together, and I will not show that table for you for now. It's a long table, and it's a very comprehensive table. So that table actually gave us some guidance, and some starting points where we can refer to when we design our own specification. So as a brief summary regarding the literature review and the survey, so information on commercially available PCDS systems as well as state DOT specifications are collected and synthesized. And also the design methodologies for PCDS was also developed by referring to existing design codes from different sources and agencies. And we found that the required drainage capacity and the pore strength should be determined considering the wall height, soil property, as well as the allowable lateral movement of the abutment. And the hydraulic property of the field fabric should be determined considering the permeability, the retention and the clogging resistance, which are actually can be obtained based on the site soil properties. And the strength of the fabric should consider the type of and the importance of the structures, since we are dealing with bridge abutments and the wind walls. So we think this is much more important than under drains and slope drains. So we suggest actually we increase the value, the requirements for the fabric in terms of the strength. And the reasonable factor of safety as well as variety reduction factors are also suggested to help us to come up with some design values. So next we select from that 87 products, we selected 4 of them, 5 of them to do some laboratory tests. And I want to mention that these tests are actually are designed to better understand these index properties of the drainage composite and to help ODOT develop future verification testing programs. And it's not designed to develop approved product list. So 5 products are evaluated from different vendors, and we did 8 tests for each one. And the 8 parameters include, for example, for the core, we tested the in-plane flow capacity, and as well as the strength, and also the thickness of the core and the fabric. And the following 5 of them actually are regarding fabric strength and hydraulic properties. So the highlighted 2 ASTM standards actually are originally recommended by ODOT, but later on we found that actually these 2 standards actually are not very suitable for PCDS. I will explain a little bit more later. So first we tested the in-plane flow of the core, which defines the drainage capacity, and we found that the presence of the fabric tends to reduce the in-plane flow rate significantly, up to 42%, which is huge. And compared to the manufacturer listed values, so the tested flow capacity actually falls short for all products. And when we test with the bonded fabric, but when we tested it without the fabric, actually the drainage capacity is much larger, and it actually exceeds the listed value. So which actually highlighted the importance of the intrusion of the fabric. So when we design it, we need to consider the effect of the fabric. And there were no significant differences between the flow rates for seeding periods for about 15 minutes and 100 hours. So the reason why we do this is to see if there are some creep effect or the time-related effect, because these are long-term service products. And the flow directions also have a little bit effect on the in-plane flow. So there are 2 major directions. One is the machine direction, one is the cross direction. So the machine direction results in a slightly larger rate. So this can help us to determine which way we want to align the product. So regarding the compressive strength, all tested values are also smaller than the listed values. And we actually found that these results may be due to the testing methods and the conditions we use. So ODOT recommended us to use the ASTM D1621, which is actually standard test method for compressive properties of rigid cellular plastics, which actually is not suitable, we found, for this. Because in this standard, they specify that the height or thickness of the sample should be 1 inch, and the loading rate should be 0.1 inch per minute. So, but the majority of the drainage composite actually are less than 1 inch thick. So in order to achieve that, we actually need to stack more than 1, okay, to come up with that 1 inch. But that actually will affect the results, right? So actually, ASTM standard committee, actually they are moving forward to replace this standard with a new one, which is ASTM D6364, which is a standard test method for determining the short-term compression behavior of the geosynthetics. So we recommend that if in the future ODOT need to test the strength, we recommend you use a new one. Okay. But unfortunately, actually, most of the manufacturers are still stick to the old one. Okay. So there is a difference. And the thickness of the core actually is another indirect indicator about the drainage. So the thicker the composite is, of course, the larger the drainage capacity will be. So a thickness is easy to check, but the tested average thickness and two different levels of normal stress are very close to each other, which is good. And for the separate core, 3 samples were received, and the tested thickness was slightly lower than the manufacturer values. And regarding the fabric, we first tested the hydraulic properties, including the permittivity, and all products also showed some lower values than the listed values. And regarding the apparent opening size, so they are significantly larger than the listed values. So these are contradictory, and this also highlighted that when we design the drainage system, we need to take into consideration about some safety factors. And the strength of the properties of the fabric, including the tensile strength, puncture strength, and the tear strength. So all of these 3 strengths are tested, and only one product shows slightly lower values than listed values, which is good. And it was found that the different manufacturers, we determine the puncture strength of the fabric using different standards. And we studied the different standards, and we suggested that ASTM D6241 is actually more suitable than the currently suggested ASTM D4333 for geotextile materials. So the difference between these 2 testing methods is actually the configuration about the loading. So the D6241 actually uses a larger puncture probe, but the other one is actually more like a pin or needle. Okay, so you can imagine which one will give you a larger strength. But we found actually from the existing study there are some correlations between them because they are both represent the puncture strength. Okay, so the strength from the red colored standard actually is larger than that, and you have a correlation to do the transformation. Okay. So from this test, we accumulated some experiences, and we also better understood the performances of these different methods. And but we do find some differences, okay, between the tested values and the manufacturer listed values. So these differences actually highlighted that we need to use a larger factor of safety when we design the system. And also, since the permittivity and the flow rate of the geotextile products actually are related, but they are both listed in the manufacturer product database, but they are actually related, so we suggest to use permittivity only, okay, when we design the specification. So after that understanding about the performance in the laboratory, we moved to the right to the field, and in total 13 projects were reviewed, and at last at the end 2 bridges were selected for side-by-side comparison. And the bridges selected actually are near here in the Dublin, Ohio, and it's at the intersection of I-270, I believe. 270 and US 33. So it's a ramp to ramp actually. So as you can see from this plan sheet here, they are next to each other, and the abutments are supported with continuous spread footing, and the bridge itself is actually steel girder with concrete decks. And an additional bridge in Ashtabula were also selected for observation of the construction of the traditional system. So first we need to design which product we need. Okay, so we, based on the backfill soil properties and also the abutment and wall height and the design methodologies that we reviewed and recommended, and a PCDS product was selected. So here, this table summarizes the key features and the properties of this design value as well as the manufacturer value. So manufacturer value should be larger than the design value. So the PCDS is constructed at 1714 abutment, and the traditional system is constructed at 1716. So in the following several slides, I will show you some animation or cartoon showing the process about the construction, so you can see the difference. So regarding the traditional system, so here's the wall, and you need to lay out or place the drainage pipe at the bottom first, and then you start to build up or place the first layer of your porous backfill behind it. So typically the lift height is about 1 to 2 feet. And then you also need to place the fabric. Okay, so the fabric right now should only cover this height. Then you start to place your first layer of the backfill, and then you compact it, you finish it, and then you actually build up your second layer of finish, and then you complete it. So note that I showed these fabric here by layers and courses. Actually, they are the same. It's a single sheet. Okay, but when you do this, you need to, for example, when you place the backfill, you need to flap it, okay, to the porous backfill, and then you compact it. After that, you flat it back, okay, and then you place another porous backfill. Okay. So this procedure, actually, you have to install these two backfills, okay, in stages, and the procedure is kind of cumbersome, and also heavyweight materials are used, both porous backfill, aggregates. They require more storage space, and the quality of the especially for the porous backfill, the 2-foot porous backfill is hard to control because it's very close to the wall and it's only 2 feet wide. So for the compaction wise, it's very hard to do. And it's also labor intensive because when you place that layer of porous backfill, typically we need hand shovels, okay, to make sure that it's about 2 feet away from the wall. Okay. And also it's time consuming because it's stage and interchanging process. And at other sites, actually, people are using other approaches to construct these 2-feet porous backfill. So at this time, so the first 2 steps are the same, but they actually can hang this fabric, okay, away from this wall with a width of 2 feet. But this can only be done by some shorter walls. Okay. So you can imagine if you have a 30 feet or even 50 feet walls, you cannot actually well control, okay, the width of this. Okay. So after this, actually you need to place your first layer of porous backfill, and then you can be more ambitious. Okay, you can place another layer, but you cannot place more because it has weight and it has a tendency, okay, to push the fabric away from the wall. So in that case, you actually have larger width, as well as have this possibility that you can destroy or damage the fabric. So probably you need to stop there, and then you place the backfill, okay, compact it until you have a better support from the other side. You can place more porous backfill, and then you can complete it. Okay. But this one, in this particular case, actually the wall is only 5 feet high, okay, so they can use this method. But still, it's staged and heavyweight material are used, so you also require the storage space. So also, we found that it's also difficult to control the quality, okay, just because the way that they place this layer, you cannot dump the porous backfill directly into that. So the way they did it is actually use a backfill. I'll show you a picture about that. Okay. They actually shake the porous backfill very gently, okay, into that narrow space, and from the bucket of that backfill. Okay. So you need an operator, okay? And also you need a coordinator to guide that guy, okay, to gently shake that down. But it's a tedious process as well. It's also time consuming. So regarding the PCDS system, the procedure is more straightforward. So the thing is, you can lay out the the composite ring, which is actually shaped to the side with rolled product. Okay? So you unroll it, attach it to the wall, and then you fasten it. So there are different ways to fasten it. So you can use the concrete nails, or you can get some help from some wood battens. Okay? So the way they did it is they actually have the wood batten, okay? So which actually passes the whole length, and then they nailed it, and then they do one more course, and then they actually cover the whole wall. So this actually completed the drainage system. And then you place the drainage pipe, collecting pipe at the bottom, and then you actually can build up your backfill. So this method is more streamlined and straightforward, and LTAP materials are used, so you don't need quite a lot storage space, and easy to control the quality and easy to inspect after you attach the wall. And also it's less labor intensive. You don't need to hand shovel the aggregates, and it's time efficient. So this is ideal, and the contractors actually like this process better. However, at the site that we do the test, so the contractor and the ODOT actually decided to place a layer of granular material between the backfill and the wall. So they wanted to have a better support for the approaching slab, but this is only optional. Okay? So this should not apply to all cases. For most of the cases, you don't need this layer. So if you have this replacement layer, actually you increase the cost, and you actually also increase the time. Okay? So remember that these commercially available products, composite drainage systems, are to replace that 2 feet porous backfill. So if you have another granular material layer, so that actually doesn't make a lot of sense. But for this particular project, actually there are some special requirements. So I will mention the differences between the cost, okay, if you have that layer or not. So here are some pictures showing the process. So on the left is you see that guy actually hand shovel that, and also you can see the heavy machines actually can run directly on the fabric. So there is a high tendency to destroy it or damage it. So this is another case where they actually hung this fabric away from the wall, and using the backfill bucket to gently shake it into this space. You can cause a lot of wasting using this method as well. So this is the installation of the composite system. As you can see, they require light space to store this rolled composite, and also it looks nice. And most importantly, we consulted with the contractors, and the feedback most positive, because it's less labor intensive and also saves a lot of time. So we also did instrumentation to see how these drainage systems work. And we choose 3 types of instrumentation. The first one is actually the piezometer in the backfill, embedded in the backfill, to measure the pore water pressure. We mentioned that when the drainage is poor, so the pore water pressure will increase, and also that will adversely affect the wall. And the second tab is actually to monitor the movement of the wall. Okay, so if there are much higher power pressure, so the loading will be high, and it may affect the movement of the abutment. And the third one is a more direct method, which we actually attach a flume instrumented with a sensor at the outlet, so we can, in the hope of measuring the drained water quantity, okay, at the outlet. But it's not that successful. Okay, for the last one, I'll show you some data. So here is the layout of the instrumentation. So the first, the left-hand side view is the elevation view. So we have 2 levels of sensors. At the bottom, we have 4 of them, and at the higher level, which is in the midway of the wall, we have another 2 sensors at each abutment. So on the right-hand side, shows the layout on the plan view. So in total, we installed 12 sensors. So here are some pictures showing the process when we install the piezometers. So the tube meter is on the front face of the abutment at the top. So we actually need to go in there with the help of the contractor and site engineers to set that up. And all these sensors actually are based on vibrating wire technology, so we can route all the cables to one single acquisition system, so we can read the data and collect the data automatically. So regarding the flumes, so there was some change regarding the location of the outlet. So maybe not that clear, but as you can see on the left-hand side, that's the elevation view. So you have that 2 abutments here. Okay. So on this side, so the outlet is here, which is close to the abutment. So originally, the outlet for this side abutment is also close to it. And now I found that it's not possible on site. So that they actually changed another location, which is much more further, okay, from that location. So here are the installed outlets. Actually, the changing of the location affected the way that we look at the data, because the distance from the wall are different. So you may have loss of the water, okay, along the way, as well as the change of the location on the road has a very small grade. Okay. So it's less steep, so it will flow. If there are water, so it will flow slower. So here are some data that we sampled during a course of 8 to 9 months. As you can see, there are some discontinuous and loss of data due to several accidents on site, including the fire on that bridge. Okay, that's very unfortunate, just on that site. Okay, but we also plotted with this. We also plotted the precipitation events that we got from the weather stations, so we know on which day you have how much of the water, the precipitation. So we saw some trends, and also the major takeaway point is the power pressure changes are very small, and the typical range are from negative 3 kilopascal to 3 kilopascal. Okay. So negative power pressure actually is good because it provides some suction and apparent strength to the soil. What we want to eliminate is positive power pressure, and when that is too much, then that will actually increase the power pressure as well as decrease the strength of the soil. So here are some close-ups about this data. And on the left is from the abutment PCDS with PCDS. On the right is with the porous backfill. So we can see that there is another trend that after a precipitation event, so the power pressure actually will increase. That's because the infiltration occurs. So the water actually seeps into the water into the soil, so increase that slightly. But later on, due to the drainage, actually all water actually are eventually drained out, so there is no accumulation. Okay? So that means the drainage actually happened or occurred naturally. And also the pressure at the PCDS abutment actually has a smaller range compared to the traditional system. And also all the different sensors gave similar readings, which means inside that backfill, actually the distribution of the power pressure are uniform. But on the porous backfill side, so you can see a larger range. So for example, in this case, during this period of time, the maximum power pressure inside this wall is about 1.5 kilopascal, but for the PCDS system is only about 1 kilopascal. Okay, so which can give us a sense that the PCDS actually will have a comparable, at least comparable drainage performance, okay, than the comparing to the porous backfill, if not better. Okay. But again, those ranges are both small, okay, so they both work well. We also measure the tilt angle. So here are the summary of the tilt angles at the two bridges, and the tilt angle at 1741 with PCDS fluctuates with a very small range, from negative 0.04 degree to positive 0.08 degree. Very small movement. And we also found the tilt angle actually correlates to the temperature very well. So that indicates that the tilt is mainly due to the thermal expansion and contraction of the deck. I'll show you a close-up view in the next slide. So in June 2017, so construction activities at the bridge 1716, which with porous backfill actually may have loosened the tilt meter. As you can see, there is a huge drop of this, but this is abnormal. This is not due to either the expansion or the accumulation of water pressure. This is just merely due to the construction activities. But if you zoom in this range or that range, actually the fluctuation is still very, very small, which can be shown in this, can be seen in this figure. Okay. So here we plotted the tilt angle versus together with the temperature, and you can see there is almost a perfect correlation between the tilt and the temperature. So when temperature increases, so it expands, so it pushes the wall toward the backfill, so you have a little bit tilt angle toward that. But when it's cold, so it will go back. Okay, so there is a very sensitive to the temperature. So with this, although we cannot rule out the effect of the water, at least it indicates that the water actually will not have a apparent effect on the tilt angle. Otherwise, the correlation between the tilt angle and the temperature will not be so good. So here is the results from the flume. So we plot the vertical axis is actually the water depth inside this flume, which will give us a sense of about how fast and how much water is coming out. And the horizontal axis is actually the time, and also we also plotted the precipitation data. So the water levels in the flume indicate drainage flow rate, and the water levels shows back after precipitation event. So after each, during each precipitation event, actually there will be a spike, which means the water level increases, indicating there are drainage. However, the quantitative data is not so reliable because there are some temperature influence of the sensors. As you can see, during one day, even though there is no drainage, no precipitation events, still you have a spike. But this spike actually is due to the temperature effect. But we actually took a detour to find this. Okay, so that's a limitation for this study. Okay, so we cannot compare the absolute value from these two flume data okay, to assess the drainage capacity, but qualitatively, they gave us a sense whenever there is a precipitation event, there will be a drainage. We also visited the site every month, so we can see in the hope that we can see some drainage events on site. But that very unfortunately, we only found one on one day there was flowing water, because we are lucky and the previous day was raining, so we can see the drainage. But most of the days we went out in a sunny day and there is no drainage at all. But we do find some evidence about the drainage, because we found these sediment trace inside the flume from these both sediments. So the sediment trace was observed, indicating normal drainage, but it's also a bad thing, because the presence of the fabric actually should prevent this erosion and the penetration intrusion of the soil. So that actually highlights the importance of the selection of the filter fabric on one hand side. On the other side, it also highlights the importance of the proper treatment of the joints and the edges. So when you construct the wall of the drainage wall, actually there are several courses, right? Remember, so each row actually have a finite width. So to cover the whole wall, you need to stitch them together. So there will be joints, okay, and that joint should be protected very well. Okay? So you need to flap the fabric from one side and then to another, and then you need also to seal that. Okay? So actually, we provided all this information to the contractor, and most of the time they actually follow that. But on the top edge, we did see some improper treatment about the edge. Okay. So as a brief summary regarding the field implementation and performance, so the installation of the PCDS is actually more straightforward, less labor intensive, and less time consuming. And the power pressures in the backfill as well as the tilt angles at both bridges were maintained at a very low level, indicating effective and comparable drainage. And the flume data further indicated active drainage at two bridges, but the data was not reliable quantitatively. And the observed sediment trees in the flume highlights the importance of the selection of the filter fabric as well as the proper treatment about the edges and the joints during the construction of the bars. So I think the most interesting part may be the cost analysis part. Okay. First, we collect some historical data. Okay. We extracted the data from the ODOT Office of Planning. So we found that actually, so here, the horizontal is the unit cost for the porous backfill systems. Vertical actually is the count. So how many occur, so, or frequency. So the majority are actually 55 to 80. And we also plotted this cost, unit cost versus its planned quantity. And we found some interesting trends. So the red color dots are representing the porous backfill system, which are currently specified method. So when your plant is small, quantity is small, the unit price is actually high. And that makes sense, right? Just like when you buy something, okay, from a tree. So when you buy more, actually the unit price actually will decrease. So we can fit this nicely with the exponential equation. We also obtained some data for the PCDS, although it's not specified, but ODOT have some historical usage of them, but only limited data are available. So only 11 points. But these points also showed similar trends, but when you have a smaller quantity, actually the PCDS costs you more. But when you have a larger quantity, say it's larger than about 1,000 square foot, so your cost for PCDS actually is lower. Okay. So that's the historical data and serve as a basis about our assessment about the current cost. And then we also tracked the cost about these two bridges. And the first table actually shows the geometry that we use to get the average unit cost. And the second table actually a summary about the unit cost of each system. And we break them down to the material cost, the labor and equipment cost, the total cost, and we with a comparison in terms of savings. So the first row in the second table is the cost for the traditional two-foot porous backfill. So the material cost is about 2.4 per square foot. Note that here we changed the unit. So previously we defined the unit cost for the porous backfill with per cubic yard because it's a volume. But since the width is actually a finite width, is 2 foot, actually we can convert that into per square foot. So we can compare to the PCDS directly. So with about $60 per cubic yard, so it will give you about $2.40 per square foot of this traditional system. And the labor and the equipment cost almost the same to the material. So it's $2.20 per square foot. So in total you have $4.60 per square foot for the traditional system. And on the second row is the drainage board with backfill replacement. Remember that we mentioned that on this particular job, we actually used additional layer to replace that porous backfill. Although it's not the number 57, it's actually still a granular material. It's not the natural soil on site. So that actually will cost you more, right? So when we took that into consideration, the total unit cost for the material actually is larger than the 2 feet porous backfill. That makes sense because now you have granular material together with this PCDS. Okay? So you have two materials actually. And then the labor actually is less than that, and we communicated with the contractor, although we didn't precisely monitor the time spent, but the contractor suggested that the construction of the PCDS was much faster and easier. So a reasonable estimate of the time saving, we took 25%, which is actually conservative to me. But anyway, so the labor and the equipment cost will be about $1.65 per square foot. So the total will be a little bit lower than the traditional system. So resulting in a 35%, which is not large. But as we mentioned, this replacement granular layer is optional. Okay? If you don't take that into consideration, so the material cost, you only have to worry about the drainage board. The drainage board costs about $1.05 per square foot. And if you took into consideration about labor and equipment, so the total will be 2.7 per square foot. So that will result in actually about 40% of savings. And then we want to see how this compared to the historical cost. And we put that 2 points onto the plot that I showed you before. So this is the current. So that black star there represents the current cost for the traditional method, and it fits the curve perfectly, which means our historical data really gave us some trend, right? And we can rely on that. And also for this red color star, it's actually porous backfill with fabric, but without considering the replaced layer. It also fits that historical data very well. And this quantity is actually more than 5,000 square foot. So in this range, you can expect about 40% of cost saving. But if you go to the Ashtabula site, which you only have 5 feet high and a smaller square footage, so maybe your your quantity will stay somewhere here, so we don't suggest you actually use that method. So that's our finding regarding the cost. So again, a little bit of a summary. To be simple, okay. So considering the optional replacement layer of granular material, so we can call this cost as the upper bound of this new method because you have additional replacement layer. So this unit total price for the PCDS system will be about 3.5% less based on the traditional method. But if you don't use that optional replacement layer, so you will have about 41% of savings. And another thing is why I'm happy with this result is we also found some historical data from other researchers. So other researchers here, I'm sorry, I didn't cite that. It's actually from Pennsylvania State DOT. They actually also compared the PCDS with some traditional porous backfill method. So they found that it will cost about 35% less if you use PCDS, and that was about 20 years ago. So I think our finding is actually reasonable. So next, we took all the information we got and all the findings we got. We want to do some recommendations and to provide some draft specifications regarding this new system. So first, we did some recommendation on the material requirements. So we talked about that the design methodology, and we know that the core, the design of the core will actually depends on the wall height as well as the soil properties. But typically, when we do the design of the bridges and retaining walls, we took some representative soil. Okay, so that's also the approach that we took. We didn't separate different types of soil for the core strength. We just took one representative soil which have a friction angle of 31 degrees and also the unit weight of about 18 to 20. So we calculated the K, which is the coefficient lateral earth pressure, and we differentiate different types of walls. So for conventional walls, you can use a smaller coefficient, but for integral and semi-integral walls and abutments, you may need a larger K, okay, based on that correlation that I introduced earlier. So with this, we also took into consideration about the factor of safety. Okay? So we come up with some numbers regarding the core strength. And for the implant flow rate, we also did similar assumptions. And depending on the wall height, we actually recommend different implant flow rate. But for the fabric, we need to consider more about the soil property. Okay. So if you have a clay soil or silty soil, so you may choose a different type of fabric. So this, we actually made a suggestion that the ODOT currently specified type A is actually, we think is not recommended for the abutment and wall drainage application. So we suggest that actual M288 specification class 2 requirements are recommended. So we summarize that in this table. So as you can see, we define the, we specify the permittivity, the apparent opening size, and the strength. Okay. And here are the values. We also recommended the construction procedures, as we highlighted that the quality control is a pretty serious issue, and also the standardized construction. If you have a guideline for the contractors, actually that we have to ensure the quality of the placement of this system. So we followed the format of the current existing specifications for other products, and we recommended the packaging, handling, storage of the gel composites on site, and also how to accept the product and how to prepare the surfaces before you place these systems. And we focused on, for example, the placement method, the joining method, okay, and the connecting to the pack outlets and the V-posts, and also the repair. Okay. We did a lot of search on other DOT specifications as well as manufacturer provided some guidance, and we got that synthesized, and we catered it to the needs of ODOT, and we had a write-up, but I won't show you everything about that. So the draft specifications so we made two draft specifications following the format of the current CMS, and we have atom 700. So 712 point something, which will be determined later, is about the material stuff, just like the fabric. So the fabric is 712.09. This may follow that. So we describe the general performance and the material requirement, as well as basis of approval. And for the construction as a whole, so this atom will be similar to atom 518, okay, which is a porous backfill specification. So we have some sub-atoms regarding the description, fabrication, material, and also this 0.05, which is specified the construction process. Okay, so furnishing and installation of this system. So our recommendations are to refine this write-up, and it can be included in Atom 712, similar to specifications regarding fabric and the prefabricated edge and rim. And for the whole construction, atom can be included in Atom 518 or as a supplement. So that's pretty much come to the end of the summary. So as a summary, so we did several things. So the state of practice regarding the drainage systems in Ohio was surveyed, and we identified the predominant systems as well as potential issues and the challenges, so on and so forth. And also, we did a comprehensive literature review regarding PCDS, and we summarized the typical properties and ranges from the manufacturers and also from other DOT specifications. We also practiced the experiments in the laboratory, and we found that some key performance parameters actually fall short comparing to the manufacturer listed values, which highlight in design we need to take into consideration about several factors. And these two drainage systems were implemented and evaluated in the field, and the PCDS system is easier to construct, to be constructed, saves labor and time. Both systems show the comparable drainage performance. And cost analysis shows that implementing PCDS can save up to 41%, but this is a lower bound. Okay, so we also mentioned that the upper bound where you need that replacement, so that will cost you similarly to the traditional method. So draft specifications on the material requirements as well as the construction processes are developed. So in the hope that it can serve as a basis, okay, for ODOT to move on to the next step. So if you have questions, send emails to research@dot.ohio.gov, and the final report will be available online in 2 weeks. And thank you very much, and I'm happy to answer any questions if you have.
Do you use this in, or you looked at it in usage on MSE walls?
Yeah, this in this particular project, that was not a MSE wall, but it certainly can be used. But there will be some modifications.
Yeah,
So,
you've got strips coming back. So what do they do?
Yeah, you will use the so-called sheet drain, which actually you don't have to cover the whole wall.
Okay.
So when you have a bolt or the reinforcement, actually you do that there, and but in between you need that.
So you don't put the strips through the material.
No. For the
you just put
at the place of this reinforcement,
yeah.
You don't have anything actually,
right.
literally. But in between reinforcements, you actually install that sheet.
Seawall is free draining, so you really wouldn't need it. The backfill for seawall is free draining.
Well, that's what we discussed, that whether it works out. So it's forced backfill. Supposed to be free draining.
Julian, you did the composite has different properties depending on wall height.
Yeah.
Is the price about the same regarding depending on wall height?
So if the wall is higher, typically you require better quality, which will have a larger strength, and the cost is, of course, is a little bit higher. But the range of the cost actually is very narrow. So the range of this PCDS system changes from 70 cents per square foot to $1.70 per square foot.
So that's those different properties are what the high end of that strength the cost range is.
Yes.
The wood batting 2x4s, the on centers in that, I mean, is that the certain locations where sedimentation is coming through? It seems like if you're shooting concrete nails to them.
So you mean the wood, the position of the wood. So they are not the location of the edge of one sheet reactor. They actually, for example, for one sheet, so you may have two wood, but not necessarily on the edge.
Mm-hmm.
On the edge, because you need to flap the fabric from one composite to another. So you can flap that so you can cover that thing. So you don't want to nail or fasten at that position because you will probably damage or decrease the thickness of the, so it will not be continuous.
But you're still shooting holes through the fabric.
Yes. Yeah. Yeah. So there are some requirements on how frequent you shoot. Typically 3 foot by 3 foot. Okay, so it's suggested we include that to the draft specification. You don't want to shoot too much nails, and you don't want to shoot too few of them.
The silt, Jake, might be coming from, they put in the tile and grate, and they laid the tile in some dirt instead of 304 or 57s. I was wondering if the silt might be coming from there.
Yeah, so initially, actually, we didn't figure out we can do the way they did it. They used that that wood spar there. They actually saved more time than we expected. We just suggested at the beginning. We suggested you just shoot nails with that frequency, but they in the field they actually found that maybe it's much easier. Okay, so if you have one row of that, you just shoot nails on that line. And another thing is to place those composites, so you don't have to place that vertically. You can do horizontally as well. So initially, actually, we recommended to do horizontally because we found the manufacturer actually recommended to do that, some of them. But in the field, actually, we found, oh, they did this way and it works. And they think that's easier and faster. So,
I could be wrong, but doesn't the backfill requirements for the unclassified excavation require structural backfill? Would we both be put 3 or 4 behind?
I'm sorry?
What, doesn't the ODOT spec require structural backfill behind the porous backfill a little south if it's under the roadway? You're saying we could do
It usually does under the approach side. Yeah, that particular project is different.
But your 203 would generally be okay right behind the streams now?
Yeah, 2 or 3. Yeah.
I think
Right,
the
Jim?
other reason they use 304 is that had a 2-foot canal to step back. And when they got up so high, they wasn't going to be able to get the rollers in for the 203 compaction. And so they used a couple foot, 2 foot of 304
Yeah.
on the plate pan, if I remember right.
At least on the wing wall, you don't have to.
That was just on the abutment.
Yeah, on the abutment. Other questions?
Okay, thank you all for attending. The final report and this presentation will be available on the research website in about 2 weeks, maybe 3 sometime. In the meantime, feel free to call us or email as well. So, thank you, everybody.
Thank you.